Alright, good morning, ladies and gentlemen. What we're going to be talking about today are complex numbers, Gaussian integers, Gaussian rationals, and Euler's equation. And this presentation is being brought to you by myself, Isaac Trostle. The goals for today are simply to talk about what the complex numbers are, what the Gaussian integers are, and what the Gaussian rationals are. In addition to that, we're also going to be answering the question of what Euler's equation is, and once we talk about what that equation actually is, we will then take it and apply it to some of our things that we talked about earlier, like the complex numbers, Gaussian integers, and Gaussian rationals. So to begin with, what are the complex numbers? We need to know what the complex numbers are. And the complex numbers are the field of numbers of the form a plus bi, where a and b are real numbers and I is the imaginary unit equal to the square root of -1. So basically a pretty easy symbolic representation is given right here. We have our c equaling a plus bi such that a and b exist in the reals. And some quick examples are 7 plus 3i, pi minus I. That's a pretty simple example right there. A number that could easily fall in this category is something like just 2, or I itself obviously falls into the set of complex numbers. And another number that falls into this set is also the square root of I. Now, the square root of I, obviously, as we kind of look at that number, it's different from the other ones simply because if we look at what we are given now, we cannot write that as a plus b in a plus bi form such that a and b exist in the reals. So that's something that we will be getting to later, but that's a current problem that we have. So if we continue on, we then move on to the Gaussian integers, and the definition of the Gaussian integers is a complex. The Gaussian integers are complex numbers expressed as a plus bi such that a and b exist in the integers. So essentially, the Gaussian integers are just a subset of the complex numbers, and even more importantly, they are actually a subring of the complex numbers. So that means like all those functions like multiplication and addition also fall under this set. So symbolic representation again is very similar. The way that we identify the set is z with some brackets around I, and again we just have that a plus bi form, but instead of having them a and b exist in the reals, this time they exist in the integers. And a real quick example of that is 7 plus 3i. Right? And then finally, in terms of our different sets of numbers, we have the Gaussian rationals, which again is very similar to the Gaussian integers, except that a and b are now rational numbers. I apologize about that. There you go. So, yeah, once again, so a and b exist in the rationals. So an example of this is like 7/3 plus 3i. So now that we've talked about our three different sets of numbers, now we're going to talk about Euler's equation. Euler's equation is e to the power of ix is equal to cosine of x plus I sine of x, where I is the imaginary unit that equals the square root of -1. So pretty simple, pretty straightforward. That's our equation that we're talking about. And now what we're going to do is we're going to prove it. So we need to show that e to the ix is equal to the cosine of x plus I sine of x. To do this, we need to rewrite both sides of our equation. So we need to show that we essentially just need to write e to the ix, and we need to show that that is equal to cosine of x plus I sine of x. And to do this, we need to, what we're going to do is we're going to write each of those equations as a polynomial. So to do this, we need to use something called the Maclaurin Series. And what the Maclaurin Series does is it takes a function and it at a specific point, and then you rewrite it such that you can have the derivatives of that function at that certain point. So if we have our polynomial of, so for instance, if we have some function written as a polynomial, our polynomial is going to be p of x. That's going to be equal to f of 0 plus f prime of 0 to the x plus 1/2 f double prime of 0 x squared, and so on and so forth. So, and the reason that this that we write the Maclaurin series this way is that when we take the derivative of this polynomial, when we take the first derivative, or excuse me, say we plug in 0 for our first value here, then everything else beyond that f of 0 is going to cancel out, because when you plug that 0 into x, 0 times whatever value you have here is going to disappear essentially. So you're just going to be left with p of 0 is equal to f of 0. When you take the first derivative of p of x, f of 0 is going to go away, and then the f of 0 prime times x, that's going to turn into just f of 0. And then basically you're going to take the derivative of each one of these little pieces of the polynomial, and everything else will have an x remaining except for this f prime of 0. So then when you plug in f prime of the first derivative of your polynomial p of x at 0, you're going to just be left with f of 0. And this would continue on as we go throughout the Maclaurin series. So what we're going to do is we're going to take this Maclaurin series and rewrite our two sides of our equation. So to do this, we need to know the derivative of e to the x, sine of x, and cosine of x. So just real quickly as a review, when our function is e to the x, the derivative of e to the x is just e to the x. For f of x, we have cosine of x, when our function is cosine of x, the first derivative is negative sine of x, then negative cosine of x, and then sine of x. So those are the first three derivatives of that function. And then when our function is sine of x, it's very similar, except we start just a little bit later in the series. So we have sine of x, cosine of x, negative cosine of x, negative sine of x, and then negative cosine of x. So we need to know the derivatives of each of those, but when we are rewriting our functions, we're going to focus on that point 0. So e to the x, when we plug in 0 for x, we get e to the 0 is equal to 1. For cosine of x, cosine of 0 is 1, the negative sine of 0 is 0, negative cosine of 0 is negative 1, and the sine of 0 is 0. And that also applies for, obviously, when we have our function sine of x. So what we're going to do is we're going to begin with the left side of our equation. E to the ix is equal to cosine of x plus I sine of x. So we're going to start with that e to the ix. So before we continue on though, what we're going to do is we're going to focus strictly on e to the x for right now instead of doing e to the ix, and then we'll add that I in later. So we're trying to rewrite our function e to the x as a polynomial. So we have our Maclaurin series written out here, and all we're going to do is we're just going to input each of those derivatives from our function earlier. So e to the x for each one essentially, and again it's at e to the 0, so we just have 1 plus 1x plus 1/2 times 1 times x squared plus 1/6 times 1x cubed, and go on infinitely many times. So we can then simplify that to this right here. All we have to do is add in that I. So essentially wherever we see an x, wherever we see an x, we're going to plug in an ix instead. We then can simplify that out to get our result of e to the ix is equal to 1 plus ix minus 1/2 x squared minus 1/6 times ix cubed plus, and continues on. So now we're going to do the right-hand side of our equation, the cosine of x plus I sine of x. And to do this, we're actually going to break this down into two parts. We're first going to work with cosine of x, and we're going to work with I sine of x. So cosine of x, again, we set it equal to our Maclaurin series. We then substitute in for our f of 0 and all the remaining derivatives. And then we simplify. Again, we do this for sine of x. Now we're going to do this for sine of x first, and then we'll simplify that to, or not simplify, but then we'll factor in our I later on. So again, set sine of x equal to our Maclaurin series. Sine of x, or we input for f of 0 and f prime of 0 and all those derivatives. We again simplify, and we're left with sine of x equaling 0 plus x plus 0 minus 1/6 cubed plus so on and so forth. Now, all we have to do to get this to equal I sine of x is multiply the whole right-hand side of that by I. So we end up with 0 plus ix plus 0 minus I, or 1/6 times I x cubed. So what we have to do now is just simply add those two together. We can combine like terms, and we end up getting that cosine of x plus I sine of x is equal to 1 plus ix minus 1/2 x squared minus 1/6 I x cubed plus, you can continue on. So if we want to look back at our two polynomials, we have e to the ix and cosine of x plus I sine of x, and it turns out that these two, when we write them as in that Maclaurin Series fashion, we have the same exact functions here. So that's why they're equal. And to kind of just emphasize a little point here, the reason that these go on infinitely, they go on forever essentially, but if you actually imagine them both stopping, you can see that they would both be equal. So we're just going to kind of take that on faith right now. Alright, so yes, we know that e to the ix is equal to cosine x plus I sine of x. So I guess the next question is, why do we really care about this equation? I mean, what's so special about it? So what we're going to do is we're going to start setting some values to x. Right? So e to the ix, we're going to set x equaling pi over 2. So e to the I times x is equal to cosine of x plus I sine of x. Plug in pi over 2. And once we simplify that down, we end up getting that e to the I pi over 2 is equal to I. Okay? So what we have is another way to essentially write pi. We can write that as e to the I pi over 2, or cosine of pi over 2 plus I sine of pi over 2. So just I mean, we already kind of knew this, but can we express I as a complex number? Of course. I mean, we can easily do that by just saying that I is equal to 0 plus 1I, right? So that follows from what we were talking about, how we can rewrite complex numbers. But going back to that question from before, what about the square root of I? That's a complex number, but can we express that as a complex number? Well, on the surface, square root of pi, we can't just immediately know, oh yes, like I can write that as a plus bi. So we have to do something to figure out how to write that as a plus bi. Well, if we look back at our Euler's equation, we know that e to the I pi over 2 is equal to I, right? So let's take the square root of both those sides, and we have the square root of e to the I pi over 2 is equal to the square root of I. If we simplify one side of that, the square root is like taking some value to the 1/2 power. Okay, when we simplify that, we can have e to the I pi over 4 is equal to the square root of I, and that's the same thing as cosine of pi over 4 plus I sine of pi over 4. So if we then simplify that down just a little bit more, we have 1 over the square root of 2 plus I times 1 over the square root of 2 equaling the square root of I. So since I over the square root of 2 is in both of these spots right here, and those are essentially our a's and our b's, we know that we can rewrite square root of I as a complex number, where a and b are equal to 1 over the square root of 2, and since those are complex numbers, we know that, or excuse me, that those are real numbers, we know that will satisfy our definition. So again, just to look back at what we've talked about here, we've talked about what the complex numbers are, what the Gaussian integers are, and what the Gaussian rationals are. We answered the question about what Euler's equation is. We've proved that Euler's equation is in fact true, and we also showed some cool applications of the Euler's equation. Thank you very much.